Okay, so we have finished the unit process uh, for IC fabrication, and in the following several lectures and in today's lecture, we are going to discuss how to integrate these processes. Specifically, today we are going to talk about IC device isolation. So we know for IC design, for IC fabrication, especially for VLSI design, there are many transistors fabricated together and next one by one. So we want to make sure the devices can operate independent to other the status of other devices. And so the technique used to do this work is called IC device isolation. So there's some metrics for device isolation module. Like we need to care about the density, device density. We want to make the device density larger, and we want to simplify the process complexity. And the yield should be higher, and the device for device isolation, we need to make the surface planar, and also we need to reduce the parasitic effects. So there are several techniques, different techniques for IC device isolation. So you have junction isolation, LOCOS isolation, trench isolation, and silicon on insulator isolation. So the junction isolation is the earliest practical method for device isolation, especially it was introduced for bipolar junction transistor isolation. So we can see here we have our planar device of two transistors, bipolar junction transistors. We have N substrates as a collector, and then we have the base and the emitter. We have two. And I want to make sure they will not affect each other. So we need to have enough space between these two devices. So basically the collector, we share the same substrate. So for the base, so the base here is actually the emitter. So the emitter automatically isolated because of the base and the collector. There's reverse bias junction, so already automatically isolated. So we need to consider the base, these two bases. So they will have a reverse bias junction, and I want to make the depletion regions not overlap each other. So, or they should not, at least they should not touch each other. So we know for the depletion, we have our depletion layer thickness, WD. So this is for device, semiconductor device, from semiconductor device. So just a quick review of this kind of equations. So you don't have to, this is not a focus for this course. So we just have some basic concept. For depletion region, there is such equation. This function like the doping, the building potential, the collector base current. And this depletion layer thickness, okay, so like it's showing here. So we have the junction here, the PN junction. So for the collector and a base, there's a PN junction, and here there's another PN junction. Okay. So these two PN junction, so they should be reverse biased, so we have all this like typically for collector concentration, ND 10 to the power 16 per cubic centimeter. And then we have this For silicon, this permittivity we know, so about 12 or 11.7, and epsilon 0 we know, and then Q we know. The building potential possibly about around 0.6 to 0.7, and then so we see the and then we can find this depletion region. And for example, so if the VBC is 5 volt, and then we can get a depletion with 1.8 micron. And if we increase to like 10 volt, and then the depletion region 2.4, depletion width is 2.4 micron. So we can calculate, and this we can define the minimum device spacing. So about so the depletion, we have two, so double should be doubled, right? So this gives idea of actually this is a junction isolation, because this is based on a p junction, the reverse bias p junction, and then depletion width, and there's no current flow, so it's automatically disconnect or isolate two devices. So to further make improvement, we can use we can make the device, the bipolar junction transistor, onto your piece of P-type silicon substrate or other materials. So NPN bipolar junction transistor and NPN bipolar junction, we have two. And on the other hand, so we have actually oxidation layer on top of this device for us for insulating purpose. And then we also have metal on top, oxide to make interconnection. And as you can notice, actually we have N, here's N, here's N, and here's N, here's N plus, anyway. So then we have actually oxide, and then have metal. This is metal oxide metal. This is a parasitic metal oxide semiconductor, not metal oxide metal. Metal oxide semiconductor, this is MOSFET actually. So it's MOSFET, and if we apply a certain voltage, actually, there will be a current flow. So, and this transistor will be on. So we need to increase the threshold voltage for this parasitic MOSFET, and so that there will be no current flow between these two devices. So this is the basic concept. And normally we just make the threshold of the parasitic MOSFET to be 2 to 3 times greater than the supply voltage, so that we don't have leaking current between the two devices. So this is also another effect that we need to consider. This is parasitic MOS transistor. So for junction isolation, it is simple process, and it is a planar isolation, and the yield is high. But also there are some problems associated with junction isolation, so the density is not good enough, not large. Especially we keep decreasing the device, the depletion. Yeah, so the depletion actually cannot decrease much. Okay, so the density of the device cannot increase because it's limited by this the spacing between the two devices. So on the other hand, if we increase the substrate concentration in order to increase the density, this also introduces another problem, that is the capacitance also increased. So we need to make a trade-off between the density and the capacitance, parasitic capacitance. So we may use gathering to improve the junction isolation. So we deposit, we just make our actually P plus barrier in this P subject. So this way the needed spacing can be made smaller, we can improve the density and decrease the device separation. This is the basic junction isolation. So a second type of device isolation is called LOCOS, local oxidation of silicon. Okay. This is the standard isolation approach for silicon IC fabrication. So we look at here, we have a source, drain, and we have one transistor. This is a MOSFET and another MOSFET. And then here, you always say this is field oxide, so in red. So this is field oxide, this is actually just LOCOS. So local oxidation of silicon. So we grow a thick field oxide before, so we use this actually field oxide for device isolation. And then we have the hole between this field oxide, and we make the device in this hole. There are transistors in this hole, and then we can have isolated MOSFET. So this technique addresses both the isolation and the parasitic device formation problems. Here we have some general steps of LOCOS process. So firstly, we have silicon wafer, and then we grow silicon dioxide using CVD method, and then we grow silicon nitride. So we use silicon nitride. Actually, silicon nitride has some lattice site mismatch between with silicon. So we use a buffer layer. This is silicon dioxide. So we deposit firstly silicon dioxide to release the stress. And then we deposit silicon nitride using CVD method. And then we deposit photoresist pattern using photolithography. And then we etch the silicon nitride. And then we use silicon nitride as our mask to etch the silicon dioxide buffer layer. And then use a thermal method to grow silicon dioxide. So this field dioxide. Of course, we remove the photoresist, and then grow this field oxide using thermal oxidation. And next, we remove this silicon nitride, and then we have silicon oxide here, and then silicon oxide. This is field silicon oxide, and the buffer silicon oxide. Okay, and then we have this region between the two LOCOS region, the two field oxide, and we make the device transistor into this small region, and then we have isolated MOSFET. So to make some more details, so we grow silicon dioxide onto substrate, and then deposit silicon nitride. And silicon oxide work as the buffer layer or pad oxide. So this is because we mentioned earlier, so this is reduces stress between silicon nitride and the silicon substrate, and also it improved adhesion between silicon nitride and silicon. And then, so this silicon nitride work as our oxide barrier. So basically, this exposed region can grow oxide using thermal oxidation method, and this region covered by silicon nitride will not grow oxide in their thermal chamber. So we have this, silicon dioxide form. It consumes like 44% of silicon, and of course, after silicon oxide formed, so the volume will increase, by like 1 time. So so this actually introduced here. There's a beak, like a bird's beak. Okay, and remove photoresist and oxide wafer. So this here, this is the beak. I showed some details of the beak. So we have field oxide, And this is a bird beak. So bird beak, actually, we cannot go device here. Basically, this is a little bit a waste. So we need to make this bird beak as small, as short as possible. Yeah. And so the good thing for LOCOS is simple process flow, and also the oxide quality is high because it's thermally growing, thermal growing oxide. And the demerits or the downside, as you mentioned, this is a very big problem. So if we reduce the device dimension, actually the bird beaks there, and still not decrease accordingly. So it with a lot of reading, a lot of so area for device fabrication. Another thing associated with this LOCOS is the narrow channel effect. Okay, so for the field doping, the field oxidation, the field oxidation causes the field implant, the implant here to diffuse into the edge of the actual radiant. So this increases the threshold voltage and reduces the driving current. So this is a problem, narrow channel effect associated with the thermal oxidation of this field oxide, because in high temperature, and high temperature leads to the P+, for example, here, underneath this field oxide to diffuse into this this region, diffuse into this this active device region. So it shrink the device, consumes some area. It's a narrow channel effect. To reduce bird's beak, so we can use a process called LOCOS. So LOCOS, local poly buffered oxidation of silicon. So we just this is a normal or standard LOCOS. Okay, nitride oxide. Instead of depositing nitride directly onto the oxide, we deposit polysilicon between nitride oxide, and then we will say actually the bird beak is shortened, and this is removed. This reduces the length of the bird beak, but still it does not solve the problem of lateral diffusion of field dopant. So the diffusion still happens because of thermal. This is still a thermal process, 1000 degrees C. Okay, and so we use another method. This is trench isolation. So trench isolation, we cut a trench into the semiconductor, and then this trench will be filled with non-conducting material, like silicon nitride, for example, or silicon oxide. So there are two types: shallow trench isolation, STI, and deep trench isolation. Okay. So for the silicon oxide, so instead of using thermal oxidation, we use actually CVD method in cellular trench isolation. So we show later here. So this here we show that some details of STI steps. So yeah, it's still like the LOCOS process. First, we need a deposit pad oxide. So using so here we use a thermal grow thin layer of oxide, and then we grow silicon nitride using CVD method, and then we deposit photospin, photoresist on photolithography, and then developer, and then we etch. So there's our trench made, yeah, and then we deposit trench oxide using CVD method. So normally we can use HGP CVD, so to deposit quickly oxide layer. Okay, and then now it is not flat anymore, so we need CMP to make it flatten. So to flatten the CMP to remove the actual oxide, and then we see the silicon nitride again. Yeah. This is okay. And then we remove the nitride using wet etching with phosphoric acid. Okay. And next, so the projecting oxide is removed by BHF, so buffered hydrogen fluoride etching. Okay. So we get to this, we get this flattened surface. So here we show some schematic. Shows the schematic with shallow train isolation module with more steps, more details. So firstly, we have nitride as thermal growing silicon dioxide and CVD nitride, and then photoresist pattern, and then nitride as mask pattern silicon dioxide, and also the silicon. So, and then here is the change edge. And then, so we expect that there's a pad oxide and a cut. And then we use actually use oxidation again to fit this and a cut. Okay, and then we use HTTP CVD to grow oxide to fill the trench. And then we add back a little bit using CMP and HF dip, and then we remove the silicon nitride. And then we will have this shallow trench isolation. Okay, and next we have deep trench isolation. So to make comparison, we can see here in this figure. So this is the transistor, and here another transistor. This is, for example, inverter. So we have NMOS, PMOS, and then we have N-wire, P-wire, and on an N substrate. So this shallow train isolation used to isolate the N transistor and P NMOS and PMOS, and then we have a deep trench isolation to actually to block this P wire from here. This is N substrate region. So make a further isolation. So this is deep trench isolation. So look at some details. So this shows SEM micrograph, scanning electron micrograph of an extreme X-ray crucial deep isolation process. So the process might be, the basic process might be similar, but it's much more challenging. So for example, we have the width around 45 nanometer to 500 nanometer, less than 1 micron. And then the depth is 2 to 5 micron, even 10 micron. This is a very, very deep, very high aspect ratio. And again, this starts from a standard LOCOS structure process, oxide, and nitride, and photoresist, and a pattern. And then here we can make it this region P type using boron implantation. And then so we form the fill this region, the trench with the polysilicon. So by simultaneously depositing silicon dioxide while etching silicon anatropically. So then we form the deep trench isolation. So another isolation technique is silicon ion insulator. You might have heard about this silicon ion insulator, SOI. So there are different type of SOIs: dielectric isolation, wafer bonding SOI, and CMOS. So let's just have a quick look one by one. So dielectric isolation, here the process. So we have, for example, we have an N-type silicon, and then we grew oxide, and then pattern oxide with the windows, and then we etch the silicon, and then strip oxide, and then we grew oxide again. So we have like here, grew oxide, and then we deposit a very thick layer of polysilicon, and then reverse, then flip, and polish the backside down until to the insulator. And then we just make the device in this insulator, in this region, in this silicon region. And then we have this dielectric isolation. So this is dielectric isolation, and then we have the wafer bonded SY. So wafer bonded XY is which is similar to the dielectric isolated. So starting wafer deposit the oxide, and then deposit the poly, and then just planarize the polysilicon, and then deposit through another oxide, and then flip and bond to another silicon wafer. Flip the first wafer and bond to another wafer, and then back grinding, basically back grinding this top, the first silicon wafer down to the insulating area like silicon dioxide, and then we can make the device transistor onto this silicon region, this insulated silicon region. So this is wafer bonded SY, and here we showed wafer bonded SY image. So we have silicon, and then silicon dioxide, and then silicon again. So and then we have the metal interconnection on top of silicon. So we mentioned wafer bonding. So wafer bonding, the process. So we do have two oxidized silicon wafer pressed together and subject to oxidizing, and it has like 700 degrees. It required pressure. Okay. We apply voltage and temperature to 11 to 1200 degrees C, and then so one oxide wafer, the one bare wafer cleaned, and rinsed and dried, and then they place face to face at room temperature. The self-adhesive contact is formed, and bonding is completed by heat treatment at 1100 degrees C for 4 hours in nitrogen. So this is a very basic wafer bonding process used for SOI. And another one is CMOS, separation by implanted oxygen. So the basic process, so we have a silicon wafer, and then we use the ion implantation. This is very high voltage, like 1 million electron volt, high dose implant. So they will not plant on the top surface, but actually somewhere below this top surface, the surface. Yeah. And then we apply a very high temperature annealing, and then we will have oxide, silicon dioxide formed, because we have implanted oxygen atom ions, and react with silicon and form silicon dioxide. And so we will have a thin layer of silicon dioxide, so into this silicon wafer. Yeah. And then we have this SOI silicon insulator. Okay, and here it shows the shows another 3D pattern. So oxygen beam ions, high energy, high dose ions implanted into silicon substrate, and then annealing and form a silicon dioxide insulator, and then we can make the device. Yeah. And so there will be no leaking current between devices. This is CMOS. I think this is yeah, that's it. So so this is isolation. And next lecture we are going to talk about contact and interconnection. So before we start the class, let's just look at what our plan. So here we show. So today is 23rd. This is Friday, and I just we discussed the lab 2. Lab 2 basically, I just follow these steps, not so much on labs, but I follow the step for you to understand how the transistor, most transistor are fabricated step by step. And then there's a small project you can work on if you have extra time, if you have interest. That is bipolar junction transistor. That's a fabricated bipolar junction transistor, maybe a little easier than by MOSFET. And so you will just review what we have learned before, the process, the unit process. Okay, and then it's due on 7th. And then we have so we have this is 23rd. And then 26, we have, we talk about contact and interconnect. And 28th, I will have the graduate student, my graduate student, to talk about, to give a presentation on their simulation. So I give the topic of synchronous two-cadre simulation of nanowire transistor, or GAR transistor, that is a gate all around field effect transistor. This is for 3 nanometer, 5 nanometer technology node, the most recent, most advanced VLSI fabrication transistor technology. So, so they are going to do some simulation using their synchronous two-cadre. So we will see. I haven't seen yet. So there's some project I assigned them to do. So we will say on 28th, 7:30 p.m. In the evening. I'll give them 1 hour to give their, maybe they will have half an hour to finish and we can ask questions. And the 30th, we are going to talk about so CMOS processing. So CMOS processing, so that is like process integration, and we take example like 3 micron or like 0.2 micron process. We show the full process of transistor and fabrication from our the back end of front end of line to the back end of line, the interconnection, metallization process. And then we have, oh yeah, 30, that's a problem. 30, actually we have the expo. This is exciting. I always exciting the expo. Of course, yeah, expo. Expo, we have no class. So you were just, yeah, so we are attend the expo, actually. Enjoy expo. And then third, so we're going to talk about this process, CMOS process, full process flow. And then we have 2 days left, so you can prepare for the final exam. Like final exam will be on, so here, this is should be like Thursday, or should be Thursday evening. If it is on Friday morning or afternoon, let's do like Thursday evening, 7:30. And VLSI design EC445 will be Wednesday evening. Some of you are now take VLSI design, so this will be Wednesday. And then this 5th and 7th, you can prepare the final exam, and also maybe you can work on their lab 2, and so if you have interest, for those who have interest, you can just work on this BJT. This is need extra energy to think about it. Okay, any questions? Good. And so see you on Monday. So a good weekend.